The National Electrical Code, Section 312.11 at WO, states that enclosed busways shall have provisions to confine and conduct any gases generated within the enclosure during fault conditions and have provision for safe release of these gases to the surrounding atmosphere only through designated pressure relief vent openings. While this code section specifically addresses enclosed busways, the fundamental principle of managing gases produced during fault conditions is broadly applicable to electrical enclosures, including panel boards or power distribution units (PDUs). In assessing a PDU design with an internal dead front, a 75 kV amps transformer, and a glastic shield positioned near the transformer taps, several factors must be considered to ensure compliance and safety. The primary function of the internal dead front, especially when combined with the glastic shield, is to contain and direct any gases that may be generated inside the enclosure during a fault. The glastic shield, with its 25 kV dielectric rating and 60 mm thickness, serves as a crucial barrier, offering dielectric protection and significantly reducing the risk of accidental contact with the transformer taps. This is particularly important given the close proximity of the taps to the shield, approximately 1/4 inch. The 1 and 1/2 inch distance between the dead front and the exterior door of the cabinet is a critical aspect for ensuring adequate ventilation. This spacing is designed to facilitate the safe release of gases in the event of a fault, allowing them to vent without posing a risk to the operator or the surrounding environment. Several steps can be taken to address concerns about compliance and enhance safety. Firstly, it is important to clearly explain that the internal dead front, in conjunction with the glastic shield, effectively fulfills the intent of NEC 312.11 at WO. This is achieved by confining any generated gases and providing a means for their safe release. Supporting documentation and evidence should be provided to demonstrate the safety and adequacy of the measures taken. This may include testing data, engineering analyses, and compliance reports. To further enhance dielectric protection, consider adding an insulated lining or spacer between the dead front and the transformer taps. This additional layer of insulation can provide an extra margin of safety and reduce the potential for arcing or other electrical faults. If an engineer remains unconvinced about the compliance of the design, it is advisable to consult with a qualified electrical inspector or engineer for an alternative interpretation. A neutral third party can provide an objective assessment and help resolve any disagreements. It is also essential to consider general safety practices within the PDU enclosure. All components must be properly rated for the intended voltage and current. Regular inspections should be conducted to identify any signs of wear, damage, or potential hazards. Ensure that the enclosure is properly grounded to minimize the risk of electrical shock. Additionally, all personnel working on or near the PDU must be adequately trained in electrical safety procedures. It is important to understand the purpose of each component within the PDU and how they contribute to overall safety and performance. The transformer taps, for instance, are used to adjust the voltage level to match the requirements of the connected equipment. The dead front serves as a barrier to protect personnel from coming into contact with live electrical parts. The glastic shield provides an additional layer of insulation and protection. In summary, while NEC 312.11 at WO specifically addresses busways, the underlying principle of managing gases during fault conditions is relevant to PDU design. The internal dead front and glastic shield, along with adequate ventilation, can effectively mitigate the risks associated with potential faults. Clear communication, supporting documentation, and consultation with qualified professionals could help ensure compliance and enhance safety. Proper grounding is also vital to provide a path for fault current to return to the source, tripping the circuit breaker and de-energizing the circuit. This helps to prevent electrical shock and reduce the risk of fire. Grounding should comply with NEC 250. It's important to implement lockout/tagout procedures before performing any maintenance or repairs on the PDU. These procedures ensure that the power is disconnected and cannot be accidentally re-energized while work is being performed. Use appropriately rated tools and equipment when working on the PDU. This includes insulated tools, voltage testers, and personal protective equipment. Additionally, the overall environmental conditions where the PDU is located should be considered. Excessive heat, humidity, or dust can negatively impact the performance and safety of the equipment. Proper ventilation, temperature control, and regular cleaning can help to mitigate these risks. Furthermore, it's crucial to establish a comprehensive maintenance program for the PDU. This program should include regular inspections, testing, and cleaning of all components. Document all maintenance activities and keep records readily available for review. Regarding the selection of the glastic shield, it's important to verify that it meets the required dielectric strength and flammability ratings for the application. Consider factors such as operating temperature, humidity, and exposure to chemicals when choosing the appropriate material. The installation of the glastic shield should be performed by qualified personnel in accordance with manufacturer's instructions. Ensure that it is properly secured and aligned to provide effective protection. In addition to the glastic shield, consider using other insulation materials to further enhance dielectric protection. This could include insulating tape, sleeving, or coatings. These materials can help to prevent arcing and reduce the risk of electrical faults. When selecting circuit breakers for the PDU, ensure that they are properly rated for the intended application. Consider factors such as voltage, current, interrupting capacity, and coordination with other protective devices. Circuit breakers should be tested regularly to verify their functionality. Fault current calculation should be performed to ensure that the circuit breakers have sufficient interrupting capacity. These calculations should take into account the impedance of the power source, conductors, and other components in the circuit. Additionally, surge protection devices, SPDs, should be installed to protect the PDU from voltage transients caused by lightning strikes, swishing surges, and other disturbances. SPD should be selected based on the voltage, current, and surge withstand capability requirements of the application. Regular testing and maintenance of the SPD is essential to ensure their continued effectiveness. The National Fire Protection Association, NFPA, 70E standard provides guidance on electrical safety in the workplace. It's important to comply with the requirements of NFPA 70E when working on or near the PDU. This includes providing appropriate training, personal protective equipment, and safe work practices. The Underwriters Laboratories AL 500 ATA standard provides requirements for the design and construction of industrial control panels. While not directly applicable to PDU, it provides valuable guidance on electrical safety and component selection. The Institute of Electrical and Electronics Engineers (IEE) offers a variety of standards and resources related to electrical safety and power systems. Consider consulting IEE standards for additional guidance on specific topics. The Occupational Safety and Health Administration (OSHA) also has regulations related to electrical safety in the workplace. It's important to comply with OSHA regulations to protect workers from electrical hazards. When performing thermal scanning of the PDU, use appropriate equipment and procedures. Ensure that personnel are properly trained and wear appropriate personal protective equipment. Identify any hotspots or areas of concern and take corrective action as needed. Thermal scanning can help to identify loose connections, overloaded circuits, and other potential problems. Regular inspections of the PDU enclosure are important to identify any signs of damage, corrosion, or water ingress. Address any issues promptly to prevent further deterioration. Consider using a desiccant to control humidity inside the PDU enclosure. High humidity can lead to corrosion and other problems. Ensure that all cable connections are properly tightened and secured. Loose connections can cause overheating and electrical faults. Use torque wrenches to ensure that connections are tightened to the specified torque values. Label all components and wiring clearly to facilitate maintenance and troubleshooting. Use durable labels that can withstand the environmental conditions inside the PDU enclosure. Keep a detailed wiring diagram of the PDU readily available for reference. This diagram should show the location of all components, wiring connections, and protective devices. When making any modifications or repairs to the PDU, use only approved parts and materials. Do not attempt to modify the design of the PDU without consulting with a qualified engineer. Ensure that all modifications and repairs comply with applicable codes and standards. Before re-energizing the PDU after maintenance or repairs, perform a thorough inspection to verify that all work has been completed correctly and that all safety measures are in place. Document all modifications and repairs and keep records readily available for review. Establish an emergency response plan in case of an electrical fault or other incident. This plan should include procedures for de-energizing the PDU, evacuating personnel, and contacting emergency services. Conduct regular drills to ensure that personnel are familiar with the emergency response plan. Consider using a remote monitoring system to monitor the PDU performance and identify potential problems. This system can provide alerts when voltage, current, temperature, or other parameters exceed predefined thresholds. Remote monitoring can help to prevent downtime and reduce the risk of electrical faults. In summary, ensuring the safety and compliance of a PDU requires a comprehensive approach that considers all aspects of its design, installation, maintenance, and operation. By following these guidelines, it is possible to mitigate the risks associated with potential faults and ensure the reliable performance of the equipment. Always consult with qualified professionals for specific guidance and recommendations.